Anybody who join us will be able to watch it later. So in other words, every single lecture this semester, both lectures, lab sessions, they are going to be all live streamed as well as recorded, so that you can watch them in the classroom at some point. Let me just set up. Hold on. Okay, so anybody who is on the other side of the Zoom, please mute yourself, because we actually can hear quite a lot of you already. So please mute yourself, and then if you have any questions, do use the chat window, and then we will have the course assistants who are going to be online on Zoom trying to answer your questions as quickly as they can. And then some of the questions, if the students, they are our course assistants to answer, I'll try to get to them later. Because if you're recording it, you're going to have all these chat notes to be recorded as well. There's a question already, but we haven't even started. But yeah, what is your question?
Well, I was just wondering if you could turn the mic up or turn the mic on.
Progress.
Hold on. What was it?
It's just kind of hard to hear in the back of the room. Right. There's a way to turn the mic up.
Let's see. So the microphone working. It just has to be closer, you mean? Oh, okay. Yeah, there you go. All right. I don't think it's going to be helpful. All right. I'll try to just speak up myself. Yes. All right. So welcome to the course. This is DSGA 1011. It is the course open for the graduate students at the Center for Data Science, New York University. And the title of the course has been evolving since I joined here in 2015. And then I just call it Natural Language Processing with Representation Learning. I'm going to call this course with that name for this semester. In this course, what you're going to learn is how to use machine learning in order to build a system that is able to process natural language text and then either classify it into one of the categories or try to produce another text that's going to be either the answer to the input question or a translation of the source text into a target language, or whatever you can imagine. In fact, we're going to touch a bit upon using all these techniques that were developed largely for natural language processing for something that is beyond natural language toward the end of the semester. We're going to, in particular, we're going to look into the music processing and also biological sequence movement. But that's like in December, so we don't have to actually go into it too much. A lot of the methods that we're going to learn are going to be based on so-called probabilistic graphical models. So we're going to try to imagine a system that tries to cope with the inherent uncertainty of the data by having these random variables here and there. Then when we have all those random variables, what we need to do is we need to be able to parameterize how those random variables or what kind of distributions those random variables follow. And then for that, we're going to rely almost exclusively on deep neural networks or the artificial neural networks. And by combining these two with the number of techniques for how to train or the estimating the parameters of these models, we'll be able to build the state-of-the-art natural language processing systems such as neural machine translation systems. So the important thing here is that in particular, because we are still going through the pandemic, as you probably have noticed, please do register for the course and then do come to the class only if you're registered in person. I'm fine, you all joining via Zoom, however, wherever you are, that's fine. But in person, because we do have a very strict capacity control here. So in this lecture room, you see that you can count the number of the chairs, then you multiply with some multiplier, and then you get how many people can show up. And we definitely want to follow that as closely as possible. And then as usual things, please wear your mask always, and you do the daily screener. If you feel sick, stay at home, all the usual things. Then if you are in the waiting list or whatnot, unfortunately, I really can't do much. So we actually had a discussion at Stanford Data Science. So we increased the enrollment by about 10% or actually 15% in order to accommodate more people. But literally, we went out of the space. We literally went out of the space. So if you're in the waiting list, let's hope that some other people are going to drop off. But otherwise, I can't really do much, unfortunately. Lectures are going to be on every Wednesday, 5 to 6:40 p.m. In the middle, we're going to take about 10-minute break because it's actually for me talking nonstop for an hour and 40 minutes, very much not easy. You now know where the lecture hall is because you're all here. And then again, we're going to use Zoom, but please do not share this Zoom link beyond the class. Okay, so you can share it with, let's say, your friends who just joined the course later on after the add and drop period. Fine, that's fine, but no one beyond that. And there will be 3 lab sessions. I believe all of you have been assigned to one of these lab sessions, right? One is, there are 2 on Thursdays, and then there's 1 on Fridays. And then these 3 lab sessions are going to talk about the exactly same content, just by 3 different people. So if you miss one of them or the one that you are assigned to, do join another one using Zoom. And again, we're going to record everything and then release the recordings as soon as they are available so that you can watch it later. By the way, it turned out that the lecture hosts actually had changed like that some time ago, a week or so. So if you looked at the old version, do look at it once more to make sure that you know where the lab session is going to be held. That actually was changed like pretty recently. And I forgot to introduce myself. I'm Jung-Hyun Cho. I'm an associate professor of computer science and data science at New York University. And we have 3 groups of course assistants. So Ilya is going to pair up with Maxim. So they're going to one group, we call it Bullet team. Dan is going to pair up with the R team. We have the U team. Jason is going to pair up with the Z1. So we don't have a pair team. And then if you have any questions from the lab materials, you can actually go down to the syllabus, and for each of the week, you know which team actually prepared the lab materials. So trying to direct the questions toward the relevant team, and then they'll be able to answer the questions best. So keep that in your mind. But of course, you're all students, you're free to actually ask anybody. That's perfectly fine. But you'll get a better answers if you do so. So we're going to rely on CampusWire quite a bit for the question answers. And if you have any questions, do ask on CampusWire. Do not email me. The reason is not that I'm not going to reply to your emails or anything like that, but because if you're curious about it, your peers are also curious about that. So if you post on CampusWire and then me or some other course assistant answer it, then all the other students can actually see the answers to that question. So let's try to use that. We will use Brightspace minimally, but for perhaps the most important thing, that is the quiz. So we're going to have weekly quiz that is going to be distributed via Brightspace. And then the reason why we do that is, first of all, Brightspace has the automated grading and everything. But the second thing is that if you only grade the quiz hand-ins from the registered students. And on your calendar, please do subscribe. Any change to the schedule is going to be reflected on the calendar most rapidly. If you compare to any other channel. So do subscribe to that one. This is actually not true. I'm not going to have anything there. You're okay. So you never saw that. All right. Grading. So this is an interesting thing. So one thing that I've been doing, and a lot of professors actually do, is to run experiments every time they teach the same course. This time, we're going to have 10 weekly online quizzes. So every week there will be a lab session. And then in lab session, together with the lecture, you're going to learn some concepts, right? And then at the end of the week, or Monday or following week, we're going to release an online quiz via Brightspace. And you have to answer all of them, or at least submit something. If you fail to submit for any one of these, you have to 10 weekly quizzes, you will fail the course. I'm warning you, and I have done so. And then there are people who know that I have done so already before. So do submit, okay? Even if you don't know the answers, you have to submit. Then there will be 10 of them. Then you will have 1 week to complete each quiz. And that's going to be 8% each. So you get, let's say, 80 scores out of it. And then there will be a final exam. Again, this is going to take the form of online exam, and it's going to take 20%. of the grade. And then how and when it's going to be released, we're going to announce it near the mid of the semester. We're still working on that one of it.
Sorry, I have a
Yes.
question. So you said, on that it says it'll be released at the end of the third lab session, but you just said released on Monday.
Yeah, so the release at the end of the third lab session is in the afternoon Friday.
Sure.
So we don't want to pressure you to work on the quiz during the weekend, so we'll try to release it in the morning of Monday.
Okay, and then it would be due like the following.
Yes, the Friday.
Oh,
yeah,
correct.
so-
So, okay. And then, like, what's the expected amount of time to take on?
Not long. It's supposed to, it's more like, the trying to make sure that you look at those concepts once more beyond the lectures and lab sessions so that you know what are the important keywords and the definitions. So that in the future, when you go out there and then use these algorithms, you know what are the keywords that you can use to look for. Right? So it's going to be very lightweight. That's the reason why we have 10 of them. We're going to have 10 lightweight online quizzes.
Will the quizzes be timed?
No, no time. I don't believe in timed exam, particularly if it's online. Yeah, it doesn't make any sense. All right, any other questions along this line? It's pretty simple grading criteria. Every week on the Monday, check the bright space. If there's a quiz, there will be about 5 to 7 questions, up to 10, but probably never. Just answer them, and then it's all online. It's open book. If you want to Google it, that's fine. Answer them, submit it. Then you do that for 10 times, and then you get 80 for it. All right. Any other questions on the grading criteria? Yes.
I'm wondering how will the final.
Me too. I'm still contemplating some options, but again, the goal of these quizzes exams are not for me to decide who I want to give A to, who I want to give B to, but more like their purpose is to give you yet another opportunity to review some of the material. So it's not going to be like well, here's 1 hour, let's try to solve as many questions as possible. But I haven't really decided on the specifics of the exams format yet. Well, we'll announce it by the let's say this semester.
So basically, we don't have any coding credit this semester.
Couple of the questions from the online quiz could involve a bit of a coding, but it's going to be pretty light. And for coding, my suggestion, of course, we're all grown-ups, right? My suggestion is that in the lab session, it's going to be almost exclusively done using a Colab notebook, and then course assistants are going to go through every single line in order to show you what is the right way to implement it, and then what are the let's say, mechanics behind a lot of mathematical, let's say, equations that we're going to go through in the lectures. And then my hope is that you're going to actually try them out yourself. Yeah, it's not like, build a classifier, let's make a leaderboard, you get, you're the first place, you get A. I won't do that, so the prerequisite courses, this is the one that has been always evolving part of it, but you definitely need to know a bit about probability and statistics. You definitely need to know about linear algebra. A bit of calculus helps, but only the differentiation, so it's actually the easier part of the calculus. And then if you know a bit about machine learning, that helps. But today, after going through the course logistics, we're going to actually cover these basic principles behind some machine learning, or at least a subset that are going to be relevant for this course. So it's not that worrying. Well, by now, you should have Python installed on your laptop. You should know how to use Jupyter Lab or the Google Colab. And then it's going to be very useful if you have installed or tried, let's say, PyTorch toolkit. Although, again, this week's lab session is going to be all about how to start up the Google Colab, how to install the PyTorch on the Google Colab, and then how to check that those things are well, let's say, installed and usable. So no worries, but if you have some experience, that definitely helps. And in the case of materials, I do have a lecture note, which is pretty outdated because I wrote that in 2015. However, the goal of this course is not to just give you the list of the recent papers that you need to read, but go through all those fundamental building blocks. So we will largely follow the order in which things were presented in this lecture notes, but my lecture is always just the written, so we'll just to see how we go about, right? There are always new perspectives via which I see the same content myself as well, so it changes every semester or so. And I do actually recommend you take a look at some of these books, and then some of them are actually available via NYU library, which is true for almost every textbook. So do take a look at some of these textbooks. Yeah, you don't have to read all this. I mean, I haven't read most of them. So, any question about the course logistics? Yes.
Is there like a rough schedule for like what would be, if you did want to read those books, like when, like, for chapters that align with different topics, or just like you look at the topics in the books?
Just look at the topics of the book. Yes. All right. Okay.
Are there any research papers we'll want to or need to read?
Not really. If there's any, I'm going to point them out during the lectures, but essentially anything that needs to be learned, I'm going to cover it in my lecture directly. And then of course, the goal is for you to go beyond what is being taught in the lectures and then figure out what are the new things. And then if you find anything interesting, you share them on campus wire so that the other students can read them together. So everyone is all clear about course logistics? Yes. So one thing, obviously, like if we follow all these university policies, now in particular the academic integrity, we can't really check easily because most of them are online and so on. So I'll just trust you. But please do not, try to answer all those questions in the quiz and everything yourself. And I won't be able to check any, but I can tell you that there were a few cases during my, let's say, I don't know, 6-7 years at NYU, where the students were indeed punished by failing the course and reported to university for this violation of the academic integrity. Just be very careful. And then there's no reason to copy your friends as answers, because they are probably as smart as you are anyways. All fine. Participation, I don't care. You come, you don't have to come. As long as you just ask questions on campus wire, whenever you're offline, whenever you're here, you ask a question, that's fine. We're not going to count the participation scores. I think that's for the primary scores. I like it probably. You don't need every university. No late work, unless of course for the extraordinary things. But if you think that you're going to hand in late, what do? You actually email me before you're late. Don't email me after, well, it's been 2 weeks since the deadline. Sorry, I missed it. Okay, that doesn't help. So email me all late. But generally, no late. Collaboration, talk to each other. That's always helpful, right? So trying to figure out what are the things that you know more than your friends, and then what are the things that your friends know more than you do, and then that's how you go about it. Pass-fail, all good. Pass-fail, if you want to do the pass-fail, just make sure that everything is done in advance. Again, a lot of students just email me on the last day when you can actually turn it into a pass-fail. A lot of them, and then I need to say yes and then sign something. Sometimes this time takes longer to sign things. So always do make a decision. Think about it all the way on, and then let me know in advance. Very important. Lastly, on the topic, so you can actually see exactly what kind of things are going to be discussed in the lecture and will be demonstrated in the lab session already in the syllabus. And we're going to stick to this schedule more or less as they are. One last thing, so we will have 2 guest lectures. One of them, I haven't actually decided who to invite. I have a few in my mind. The last one is going to be from Kunu, who is a senior research scientist at Python. So he's going to actually tell us about how to use machine learning or NLP techniques for modeling music. And also how to make TikTok ideas. All right, so that's it on the course logistics. Is there any questions about the course logistics or the course itself that was not clear? I'm sure it was all clear. Okay, very good. Then let me actually change the sharing. Yes. I really wasn't kidding when I said that, they're going to just use the writing. That's actually really the case. So when we think about machine learning, so we're going to talk about machine learning today. Actually, we won't talk much about the text or the natural language at all, because there has been historically about 3 stages of development in natural language processing. Now, you can imagine that in the very first stage, that was quite some time ago, people thought if we knew what language was, and then that is studied by linguistics, then we might be able to actually write down exactly how language should be processed. And then that's how usually the algorithms are written down, right? Computer scientists, what they do, we sit down, we look at the problem statement really, really carefully, and then trying to come up with an algorithm just want to solve that problem. And then we want to analyze its computational complexity, and then based on that, we want to improve it further and further. Now that's what people try to do at the beginning. Turned out the natural language is actually much more complicated than we thought. There are so many competing theories behind how the language came to be, how language is used, and so on. And then it turned out that's actually true for a lot of other problems as well, right? So something like driving. We all drive very easily. We all know how to drive easily. And then, if you don't, you'll learn it in 3 days. Let me just try to mute anyone. It's all fine, right?
Yeah.
All right. Okay. All right. So yes. So that was the first stage. Like the driving, you can do it. Language, you all speak very, very fluently, and you didn't have to know much about the language, and then it feels like, oh, I speak language. I can say Korean perfectly, so I probably know how Korean works. Turns out that that's not the case. So the first stage kind of failed in large aspects. In particular, aspect that it failed was that they failed to actually make any useful systems, anything that can solve the real problem. Now the second stage was more like, okay, so what are missing, right? So why did the first stage or the first attempt fail? Is because we know we still I wasn't there, so they still believe that they knew quite a bit about language, but they kind of acknowledge that there are a few bits and pieces here and there that we don't know. So what they did was to, okay, let's rely on these machine learning algorithms to fill in those gaps. So something like, well, any sentence or any written text should have some kind of, let's say, hierarchical structure on top of that, and then we have a lot of theory about it. But then we don't know how to infer that automatically. So that part we're going to use machine learning. That was the second stage. But again, the second stage also has failed in a sense that it was working much better, but then it wasn't really solving the problem to a degree that we wanted it to solve, or that we wanted it to the degree that we can actually comfortably deploy. So the third stage, which we are now in, is where, what if we start from scratch, and then let's rethink how we approach the problem. And then it's similar, and then it turned out that it's similar to very many problems that we don't know how to solve, but we somehow solve very naturally ourselves. Like driving, riding a bicycle, walking. It turned out that we can walk really, really naturally, very easily, right? This is one of the first things that babies learn to do. But then making a humanoid robot that's going to walk just like us, impossible so far, right? So then, what is the way for us to go about is that we know that there is a solution because we are here, and then that's the case with the natural language, or walking, or driving, or whatnot. And then we have the data that reflects what we do, how we solve the problem, but we don't know how it was, right? It was produced, and then you're going to now rely on machine learning, a set of tools in the machine learning discipline to automatically reverse engineer how we actually solve the problem, how we speak, or how we write, how we read, and so on. That's the reason why we are going to talk, we need to talk about machine learning really, really carefully. Because that's the only tool that we really have in our pocket that we can actually use. So when we think about machine learning, of course, machine learning is gigantic. It has, in fact, a longer history than computer science. So the very first so-called machine learning, let's say algorithm or the concept can be traced back quite a bit into the 19th century or not. But if you think about the modern computer science, we can only trace back to like beginning of 20th century. So it's a very historical discipline, at least in this engineering this area. And in our case, we're going to look into so-called deep learning. And deep learning can be thought of as a subset of the tools or the algorithms within machine learning. And then, as the name suggests, we're going to build something really, really deep in terms of computation. And then, obviously, how we do that? We don't know how to actually write down this computation, so we're going to learn from data how to make the kind of deep computation. So when you think about deep learning, we need to think about 5 things before we can actually start building a system, collect the data, train a model, and then deploy it. The first one is so-called model parameterization. Model parameterization refers to building some kind of, let's say, black box system that's going to take this input, whatever the desired input is, and then predicts or the outputs the desired output according to the specification of the problem. And then now the next step is to defining a loss function. Because we don't know how to make the perfect algorithm ourselves, we have to at least have an idea or way to tell whether this black box model is doing well or not. And then that's what we refer to as loss function. The second thing that we need to consider is the optimization. Now, this black box or the neural network is going to have millions, if not billions, of the parameters, small numbers that can be adapted for solving problem based on the data. And then we have a loss function. Now then, let me actually try to see if we can mute anyone who's joining the meeting. I thought I set that on, but okay, so I'm going to just mute everyone. And then let's hope that our course assistant can answer any question coming out of over the Zoom on chat instead. My apologies, I'll try to fix it next week. So optimization is okay. Now I have a loss function. I have all those, let's say, moving knobs in this model that we have parameterized. What is our right way to change this parameter so as to minimize this loss function? Right. So that's optimization. And then the second thing is the next thing is called model selection. There are many different ways to build these models, and then there are many different types of the optimization algorithms we can use. Then obviously there are many different ways to define a loss function. And then we just combine all these together, and then we call it model. So it's a bit overloaded term, but it's just a similar term. Then we need to decide what is the best strategy, what is the best combination of optimization algorithm, the choice of the loss function, and the choice of the model is. Then we need to do the model selection there. And final step, or the final consideration is reporting. We're not going to go into too much details about the reporting in this course itself, but this is actually one of the most important aspects of machine learning or deep learning. Is that now I've done everything so far. I have selected the best model somehow. Now I need to be able to tell people and myself how well this model is going to work in the wild. Now that's the reporting. And then this reporting turned out to be almost as difficult as, if not more difficult than all the other steps, because this reporting is extremely problem dependent. Depending on what kind of problem you're solving, reporting has to adapt to that. And then there's no like the set criterion or the set method that you can follow in order to report how well the model is going to work. Now, let's go through this one at a time. Let's start with model parameterization. In our case, we're going to follow so-called, I just made up the name, so don't worry about it, but it's a probabilistic formulation. What we're going to do is that we assume that the problems that we're solving do not have the answer. There is always an inherent uncertainty in the data, as well as the process by which the data was created. And this uncertainty actually shows up quite often in real life. When I try to explain you what this parameterization is, I could have chosen from, let's say, any one of hundreds different ways in which I can explain. That is the kind of uncertainty, and I somehow chose one particular explanation, arbitrary, right? And then that arbitrary nature, it is in fact a randomness that we cannot really reduce. So we're going to say that, yeah, there is just some uncertainty whenever we see the data or whenever we consider the process by which the data was created. And then, how are we going to incorporate it? Is that we're going to make a distribution rather than a function. When you think about machine learning algorithms or the research models, we often think about those models as a mapping from input to the output. And I think that that's a function. But as we just talked about, that example of having many possible answers tells us that it cannot just be a function, because function needs to map to just a one point, right? So what we're going to do is we're going to say, instead, we'll say answer. So y is going to be our answer or the output, right? And then x is input. But what is being output by our function here on that is going to be a distribution over all possible answers, given the corresponding input x. Then what it tells us is that in fact, you can imagine this as having a neural net that takes as input both the input and potential output and gives us a single scalar. And the single scalar tells us what is the likely, or how likely is that particular answer is given the input x. There are many different ways to actually model this. So in a sense, it doesn't really tell me how I'm going to use the neural net, right? So that's where we talk about the parameterization. So this is how we view the problem, is that we're trying to figure out this conditional distribution, but how are we going to actually parameterize it is this model parameterization. There are two things you can imagine. One way is a very naive approach. We say that the P of y given x is proportional to the exponential function of some function f that's going to take as input both x and y. We're going to look at actually the specific instantiation. We can just imagine that if given a pair of x and y, and then what is the score? You get a single score, but the score is not necessarily going to be probability. So we want to turn that into probability or density by exponentiating it and normalizing it. So this is a proportional to, so that when you integrate over all possible y's, you get 1. But this turned out to be a bit naive and then doesn't really help us, in many cases where the f is not too complicated. So another way to solve this problem, which we will actually go through in about 8 weeks, is the Latent variable model. In this Latent variable approach, we're going to explicitly introduce a random variable that captures this inherent the uncertainty. So we say that it's going to be P of not only y, but also z and given x. So what we're saying is that there is a deterministic mapping from x to y, except that for every choice of z, the deterministic mapping changes. So you can think about this z as, let's say, whether you're, for instance, right-handed or left-handed, right? Let's say I'm driving on a highway, and there's a car that is driving super slow in front of me. Now I want to pass this car. Now I have to decide whether to pass it via left or pass it via right. Both of them are correct, like equally correct. So then, what will change? What is this inherent uncertainty that's going to allow us to choose one of them? Perhaps this uncertainty is just a right-handed. I'm right-handed, so I'm like, maybe I have the tendency to pass it toward right. But in the data, we won't have that, right? If I collect the data of me driving, I'm going to have how the world looks like, and then what kind of decision I make, right? So did I go right or left? But then, no, I'm not going to tell the people which I just did, that I am right-handed. So that's the kind of inherent uncertainty that we're going to explicitly model with this Latent variable Z. In which case, you can think of it as we're going to have a neural net that's going to take as input not only x, y, but also z, and then output a single scalar. And of course, in this case, we need a so-called prior distribution as well. So what is the distribution over this inherent uncertainty, the Latent variable z given x? Then that one we can have another function, let's say f prime, that takes as input only x and z. All right. The first one looks simple. Second one looks slightly less simple. We'll cover both of them, but let's start with the very first because that does look simple. It does look simple. So we'll take one example. What is the simplest possible example that everyone teaches at the beginning of their semester for any machine learning related course? Course classification. So we're going to look at multi-class classification, where the output or the answer y is going to be one of the c many classes. Then our f of x. So let's just look at this one. Our f of x, f of x and y is going to be wy transpose. So this is going to be a vector. Then you have some feature of the input plus e of y. So this e y. Then this is going to be just a scalar. Then this is going to be a vector d. And this feature vector is also going to be r. So what it says is that when the input comes in, we extract some feature of the data, right? That input, and then compute the dot product against this class-specific weight vector, wy, and t is just transpose. And we're going to add a scalar that we call it as a class-specific bias. Then this is going to be the score given to this pair x and y. Okay, and then how do we get the probability out of it? It's going to p of y given x. So recall from here. So this is what we have just defined, this f of x and y. So we turn that into the probability, that is probability of y given x by using so-called softness. Transpose p of x plus dy, and then we're going to divide it by the sum over all possible classes. So the scores that are going to be given, or exponentiator scores that are going to be given to all possible classes, in order to ensure that these probabilities are going to sum to 1 when we compute the sum all the probabilities for the class. So doing this is really simple. This is exactly what you have learned from every possible, let's say, machine learning courses that you have taken so far. But this is really like one of the key ways in which we're going to parameterize whatever the natural language process model we're going to do. Too easy, right? Too easy. Yes. So we're going to look at slightly more complicated version. That is, we're going to look at this Latent variable formulation. In this case, we're not going to really look into the one that we're going to use later on ourselves, but it's going to be fun to just think about, okay, what is a raw way to view how deep neural nets are used? It's not that we just put a neural net and then we say that the problem solved, but neural net is really just how we implement or how we compute these quantities such as the probability. And then outside it, we have a lot of framework, a lot of things that we need to take care of, such as the loss functions and whatnot. And we're just trying to emphasize that point. So let's think about so-called mixture density network. Since there was a question about the papers, this mixture density network was proposed by Chris Bishop, who wrote that the amazing textbook in 1996. And then this mixture density network is used to do so-called to solve the problem of regression. So unlike classification, in regression, output can have infinitely many classes, right? And just be any real value. But then the difficulty there is that what that means is that the output distribution can be as complicated as it can be. Right? So the complexity of the distribution can be infinite as well. And the mixture density network is a very nice way to capture that one. So the output in this case is going to be just d-dimensional vector, any d-dimensional vector. And we're going to introduce the Latent variable. Then this Latent variable is going to take one of the C many possible values. So if C were just 2, you can imagine this Z as is Professor Gangenjo right-handed or left-handed? Imagine it like that. And then our way of writing the f of x, y, and z is going to be y. So that's what we want. That's what we want to score, right? Minus w z mu. I'll just call it mu. P of x. P of x is again just a feature of the input. And then we look at this difference. So the score given to x, y, z, this triplet, is going to be how different our prediction. So this part is a prediction, right? So we have a P of x, there is a feature, and then we have a Latent variable configuration specific, let's say weight matrix W, and then whatever gets out, we're trying to see how close the prediction is to the value that we want to check the score of. If they're very close, we're going to say, oh, this value can be, let's say, close to 0. If they are very, very far away, then we have the negative sign there. So this score is going to be very, very low. Once we have that, we need the second component in this data, like before. So we need to parameterize f of x and z. And in the case of f of x and z, we're going to use exactly the same thing as a multi-class classification. So we'll have a Latent variable specific W transpose P of x plus the bias that is again Latent variable specific. So I'll just put it as a, in this case, this one is going to be R defined by P because our feature vector is d-dimensional and then y is d prime dimensional. Then here as well, we're going to, this one is going to be RD and then this one is going to be this. Yes.
So what's mu on these variant?
Oh, mu. I use the mu here just to distinguish this one. This W. It's too many W's. All right. So once we have this, now let's try to write down this probability of y given x. Now, we're missing z here. So what are we going to do about z? So one thing we know from the definitions of the conditional probability is that we can marginalize out z by trying all possible values of z of the joint distribution. So this is what we are going to do. And then to do that, we need to write it once more, again, relying on the definition of the conditional probability, P of y given z and x times P of c given x. Then what we know is that we now know how to turn these score functions f, let's put the prime there, score functions f and f prime into these p and p, right? So the probabilities, that's exactly what we did here. Right? We just make sure things are non-negative and normalized to 1. How we do that? We do the exactly same thing as before. So the z from 1 to c. So we're going to sum over all possible cases of c. And then here, we're going to look at the exponential of w z transpose b of x plus bz over sum c prime from 1 to c x of w z prime transpose b of x plus b of z prime, and then this is going to be the higher times the x of minus between y and mu c p x squared over, now this time because our output y is continuous, we use the integration instead over, let's say, RD minus y prime minus w c p of x squared d of y. So what that means is that at the end of the day, we end up with the same thing, right? We end up with the same thing, but by considering different possible values of this unobserved, right? This latent, as in, we don't know what value is. By trying all those values, we actually can get suddenly a very complicated distribution over y. So you can imagine that the y was going to be the steering wheel angle when I was driving. You can imagine that this part tells me what is the chance that this driver is left-handed or right-handed. And then for each case, so whether they are right-handed or left-handed, you're going to say that this distribution is centered on the, let's say, either on the, let's say, positive side or the negative side of the steering wheel angle. And then suddenly now my probability distribution over y given x is bimodal. I have 2 points, right? So we can actually model arbitrary complex distribution over y. So this is the mode of parameterization. And then throughout the semester, we're going to learn a few different ways to parameterize this kind of these distributions for different problems in natural language processing. But at the end of the day, what we notice is that it's really almost impossible for us to go beyond these two paradigms that we just talked about. Any questions there? You go, yes.
Are the P's in the X, Y, Z and XZ the same?
Oh, this phi of x. Yeah, phi of x is, let's just assume that that is just fixed. So what do I mean by fixed? You can imagine that let's say I build the object detection, right? So I build a classifier that's going to look at a picture and then see how many ships there are in the picture. Now you can imagine that you can just give the pixel values as it is. That's going to be one way to get the phi of x. Another way is that maybe you can run some kind of object detector a priori and then say that it's just a set of ship, or the cat, dog, and so on. Right? So that's just it's going to be up to us to decide. And in particular, for natural language processing, in particular, next week we're going to talk about what is the usual way for us to featureize the inputs. Any other questions? So everyone is all fine with the model parameterization. Oh, there's a question at the very end.
Does Z have to be discrete in all cases?
That's a good question. So does Z here, the Latent variable, does it have to be discrete? The answer is no, it doesn't have to. Now there are some reasons why sometimes we prefer discrete Z, but generally we actually prefer continuous Z. Just that I chose a mixture density network here, and then that's the reason why we use the discrete Z. But some of the Latent variable models that we're going to cover later in the course, we are going to use continuous. All right. Any other questions? Yes.
Is there a different B for every Z?
Yes. So for every Z, which can take a value between 1 and C, for every Z, we're going to have a separate WZ and then BZ. But of course, you just stack them and then you get just a one matrix and a one vector. So far, so good. So we've just looked at the very first step of machine learning. It's actually complicated, the whole, let's say, pipeline. The second thing that we're going to go into is the loss function. The reason why we are going to stick to this probabilistic formulation is because once we have a probabilistic formulation or the probability distribution over y or whatever we want to measure the probability of or the predicted probability of, the loss function is naturally defined. We don't really have to do anything that is special. I mean, we could, if you wanted to write a paper instead of solving a problem, then yes, we should always come up with some weird ways to come up with a defined loss function. But if you're actually solving a problem, we have the probabilistic formulation gives us, without any effort, the loss function automatically. Now, with with let's say this kind of let's say probability formulation in our mind, so our neural net or machine learning model is going to give us the probability of a some y given the input. So this is what our neural net is giving us. Then what do we want to do? What would be a good way to tell whether the neural net is good or not? Very natural answer here would be, or maybe somebody wanting to answer, so I'll give you some few seconds to think about it. So what would be the most natural thing to use to tell whether your model is doing well? Accuracy is good, but the accuracy has nothing to do with the probability, right? Likelihood. So likelihood is one of the most overloaded terms in machine learning. So what do you mean by likelihood in this context?
Similarity between those two and
Similarity, I mean the similarity between output and the true output, okay, sounds good, but again, I don't see any similarity here, I just see the probability, right? So what we want is that if our model is assigning high probability to the correct output given the input, then we will say that's a good model. If it does not do that, then we're going to say that's a bad model. So the loss function naturally becomes the negative log probability of the correct answer given the input. So we are going to say that for each example, for each x and y star, so I'm going to use y star to indicate that this is the ground truth correct answer. A correct answer, right? So it doesn't have to be the correct answer. A correct answer. So for this, I'm going to say the loss. So the L, I'm going to use the loss is defined as a negative log probability of y star given x. So given some input and a correct answer to that input, we're going to look at the probability that is assigned to the correct answer by our model. If that's higher, that's good. If that's low, that's not that good. But the unfortunate thing is that it's just a historical reason. Optimization people always want to minimize. I don't know why, it must be some kind of psychology, but they want to minimize it, so we call it loss. Thereby, we have to call it negative log probability. So there are one more mystery here, right? So why are we looking at the log? Is log necessary here? What if we just look at the negative probability? Does anybody actually know the answer to this question? I always ask myself, and I still don't have the answer yet.
further away, the log is higher.
Further away, the log is higher.
Further away from true.
But isn't log monotonic in the sense that it doesn't really change? Yes.
Isn't it the probability is between 0 and 1, some log is negative, and then you just look at.
Yes, but the idea, why not just using something between 0 and 1? Because of the floating numbers. But I can tell you that even with analog computers, they're going to use log.
Is that because you can just add up the loss instead of one?
Yeah, that's actually a good answer. That's actually a good answer. So I'll repeat that. So now this one, so I'll repeat that shortly in a slightly different context. So this one is for one example, right? But one example does not let us actually identify this probability well enough. There's just not enough, let's say, examples, and it's just like how you learn as well. More examples you see, better you can actually answer the new questions in the future. So we don't want to just look at a single example, but we want to in fact look at many examples, millions, if not billions these days. So what that means is that this we can refer to as the per example loss needs to be somehow aggregated into the loss for the data, right? So data set level loss. So we're going to assume that we now have a D, so that's going to be the data set, the training data set that consists of the many x1, y1 star, many pairs of the input and the corresponding correct answer. We'll just assume that we have n many of them. N many of them. Now, in this case, we've been thinking about everything from the probabilistic perspective so far, right? So we can do exactly the same thing. What if we look at the probability of this data set? What is the probability assigned to this entire data set? And then perhaps, and then we can assume, now this is where I don't know if you probably have heard about it, the assumption that these were drawn independently from the identical distribution, right? So if they are independent, then it should be just a product of probability assigned to all these examples. And then we're going to rewrite it a bit, saying that it's going to be, because we're talking about the supervisor and input-output mapping, probability of the y and star given xn times p of n xn, then we'll just assume that this is unique. So we don't really care that much about how likely the input is. We only care about this mapping, right? So given this input, what is the distribution over the output, and then what is the probability of the correct output, right? So that's what we care about. Fortunately, when we look at this, so this probability is, yes,
Is that straight or is that
n. That's n.
at the bottom?
N. All of them are n. As we just learned, probabilities are often between 0 and 1. I say often because we're not necessarily saying that the y is discrete, right? Y could be continuous, and then when we are talking about continuous variables, then the density can very well be greater than 1. But let's forget about that kind of general cases, and we're going to say that okay, probabilities are well normalized so that they're always going to be between 0 and 1. If we multiply the number that is between 0 and 1 over and over, we actually exponentially converge towards 0. So that actually does bring in a lot of issues computationally or numerically. And at the same time, having a product is always a bit of a problem, which we're going to talk about it hopefully in a couple of weeks. So instead, we're going to look at the log probability of this data set. And the nice thing about the log is that it is going to turn the products into the summations. Yn star given xn plus some constant. This is just constant because we assume that the distribution over x is just uniform. We don't really care. And then what that means is that p of xn is just some constant c, right? That is between 0 and 1. Then log of that is still going to be constant. So a single value across all those examples. And then what you notice here is that each and every term within this summation is precisely this per example loss or the negation of it. So what this tells us is that the loss function that we're going to use given the data set, that single example, is going to be the sum of the per example loss functions that we have. So imagine just having a negation here, and then suddenly this whole thing, the loss that is a negative probability of the data set assigned by our model ends up being the sum of the per example loss function we have just defined across all the examples. And it's really nice in the sense that because as long as we can make our neural net output this distribution over the answers, right? Over the answer given the question, this one just works. You don't have to think too much about how to check the similarities between the different outputs and so on. And then how we actually define those similarities is going to be based on how we parameterize this probability distribution. So that's a loss function. Then, now of course, we need to look at some examples. Now let's see. All right, so why don't we take 5 minutes break, and And then we'll come back at 6:07, and we're going to look at some examples of how this loss functions actually manifest itself and how it admits the optimization. All right, let's continue. Before we continue, is there any question about what we just talked about? All right. There's almost no. So yeah, this is actually an interesting question. So the question is on the screen. What does it mean? And then why do we assume that this P of X is uniform? So here, The interesting thing is that we actually don't have to assume anything about it, and then yet sometimes we might actually as well want to reweight the examples if we have any domain knowledge about the examples. But the big assumption that we have about this data set is that this is a set of samples that were drawn from a single distribution, and each and every one of them was drawn independently from the distribution. What that means is that without knowing anything about the problem itself, and then the deficiencies or the defects of the data collection procedure, there's actually no way for us to actually prefer one over the other. So we should just treat them all just equally. But you can, in reality, it often helps to kind of, let's say, downweight, or in a sense, you can imagine that if you set this P of X and Xn to be 0 for some example, then you can use that way idea to kind of remove some of the, or the downweight it very much so that you can remove some of the noisy examples if you know how to detect them all. We often don't, but that's definitely a possibility. Any other questions? Yes.
One question. So I mean, how do you call what complete find is it generally comparing to the one language? Is it generally applicable to the others, or is can you try to code it specific language?
Right. So the question is how. So whatever that has been tested or tried for one language, how well does that transfer to another language, right? So the knowledge that we have gained or the algorithm itself. I can give you, maybe of course it's impossible question to answer like directly, but I think I can give you a couple of the anecdotal examples that might, give you some idea about what the answer is. One is that I was actually one of the very first people to build a so-called multilingual machine translation system where we built just one system that's going to be able to translate from many different source languages to many different target languages. And I don't speak any of those languages that I ever worked with myself. So that probably says a lot about how these algorithms are treated language agnostic, in a sense that you can actually come up with an algorithm that works well for languages that you have absolutely no idea about, right? However, that's not the whole story. In fact, in particular, when it comes to representation, how we're going to represent the input or the text actually does impact the performance of these language models or the NLP systems part of it. And then the optimal way in which we represent this text often is a function of a language. So if I'm trying to build a Korean natural language processing system, and I'll choose a different pre-processing routine in order to represent the text in Korean, then what I would do if I were working with, let's say, English, if I were working with Chinese, then the process that I'm going to follow in order to represent the text is going to be again different. So in a sense, the answer is yes and no. But we always strive to come up with an algorithm that is as generalizable as possible. Doesn't mean that we are always successful, but that's how it is. All right, so now we know the core principle behind defining a loss function when we use a probabilistic formulation. That is, we look at the negative low probability assigned to the correct answer given the input. If that value is low, that's very good. If the value is high, that's very bad. So we're going to try to minimize. But let's see what that means in the context of the multi-way classification. So if you recall, P of y given x, we'll just write the low version of the in the multi-way classification is wy transpose P of x plus by minus log sum. We're going to try all possible class labels exponentiated, let's say the function that we parameterize, transpose P of x plus by. As we just talked about, y can take one of the c many values, and then this is identical to f of xy. And in this case, what is our loss function or the per example loss function? We're going to simply put the negation here. Negate it again. And we say that we look at the log probability of the correct class. Right? So each example in the data set, we know what is the correct class to which x belongs. And we simply look at what is the probability assigned to the correct class given this x by our model. Look at take the log of it. Then this is going to be our per example loss function. In other words, if we know how to parameterize the p of y given x, that just is exactly how we're going to define the loss system. And when you look at this, it's actually pretty interesting. So let's just divide this into two portions. So the first part is going to be here, then the second one is going to be. Let's just imagine that we're going to look at only one example, and then we want to try to minimize this negative log probability of the correct class with x. Now, what happens with the very first term? So this first term is, let's forget about this b for now. This first term is computing the dot product between the weight vector that is assigned to this y star, the correct class, and the feature vector. Now, what does the dot product compute? Dot product computes two things, right? One is the magnitude of these two vectors, and then two is the angle between these two. If they are well aligned, the value is going to be b. If they are, let's say, pointing to the orthogonal directions, it's going to be 0. So what that means is that if I want to minimize this whole thing, which is same as trying to maximize this thing, this dot product, and then we say that this feature vector is given. Then what we want to do is to make sure that this weight vector that is associated with the correct class to align better, and then make it look similar to this feature vector. And then what this b says is that even if I didn't see any x, even if I don't have any idea about x, I want, if the y star was selected at this once in this example, that probably means that I need to score this y star high. So I need to make this b value high in order to lower this first term. What is this second term? So second term showed up automatically from the normalization procedure, right? So we wanted to make sure that the probabilities all sum to 1. In fact, it doesn't even have to sum to 1. It can sum to just some value. And then this came from the normalization. And then what does it do? So we want to minimize it, right? But we have the plus sign here, so we want to minimize this whole thing. Now, log is just a monotonic function, so we don't really have to think about whether it's log or the original function that we're trying to minimize or maximize. So we're going to look at what is inside this logarithm. So we have summation term, and then we want to lower the value of this. Now let's look at just one of them that is not necessarily y star. Right? What we're saying is that in order to lower this, what do we need to do? We need to make sure that the alignment between this weight vector assigned to a class, right, doesn't have to be a class, and the feature vector to be lower, should be aligned with. So we're trying to make this weight vector different from the feature vector. So here, the first term is going to make the weight vector of the correct class to be similar to the input or the representation of the input, while the second term is ensuring that every vector assigned to every class becomes further away from the input vector. And then they're going to just balance them out, right? And then this whole thing, in fact, does encode the notion of the similarity, right? So earlier, when I asked the question, one of the answers was about we need to define a loss function based on the similarity. But, and then it turned out it is indeed doing it already. By parameterizing the p of y given x, that distribution, we actually automatically get this measuring the similarity and then trying to make that predicted answer, and then the correct answer to be similar to each other automatically in this representation space that is a vector space. So that's a really nice thing about this whole as a probabilistic framework, and then trying to use the negligible probability of the correct answer as a per example force function. Any questions about this? This is like super important because this is how you learn all those vector representations of the words, sentence, and whatnot. And then this is indeed the entry point of further research.
In this case, when you say something is similar to something else, is it like the distributions are similar or like
So similar as in this class. So you can imagine that you can think of it. So what this says is that the vector that is associated with the correct class should look exactly like the feature vector is. Now what that means is that if my model's prediction was not y star, right? That means, and then some other class, that means that the weight vector associated with the incorrect class is more similar to the feature vector in the sense of the dot product, right? And then what we want is that if we want to avoid that one. We want to ensure that the similarity between the representation of the correct y star is more similar to the input feature than the representation, the vector of all the other classes. So in that sense, the similarity in what is outputted by the model is same as similarity in this kind of representation in the vectors.
The green part, the 10 vectors are going to be in a line, right? To increase the alignments. But aren't those in the pink area going to be actually opposite directional?
Yep, so that's the point. Here, we're trying to make this weight vector associated with the correct one to align better with the input feature that is the P of X. Here, for all the classes, we're pushing them back away.
Maybe going all the other way around.
Yep, it's okay. It's actually better. If there is incorrect, all of them except for one is an incorrect. So it's actually perfect. That's the intention.
Why do you need to take
Oh, this one, the complication looks super complicated, right? It is indeed, the so-called log sum exam, it has some issue with the numerical stability, but we'll see that there's absolutely no reason for us to actually compute this ever. So it's fine. If you wanted to compute it, yes, we can compute it. We need to be a bit mindful about numerical precision, but we rarely compute this quantity.
why can't you just take off that?
Oh, just removing this exponential. Oh, that one doesn't work unfortunately because the probabilities have to be non-negative. And then how we parameterize this f function is not guaranteed to output only the positive number. Now then, of course, the question is, okay, do you have to use exponential function? Can we use square or maybe absolute value or some, let's say, random function that it has the, let's say, positive that maps the positive side of the real value? Okay. Yes, you can. But there are both mathematical and philosophical reasons why we prefer exponential function, because that is so-called maximum entropy formulation. And then choosing this formulation is always a good idea unless we have some knowledge about the problem itself so that we can actually choose some other function. That is rather philosophical, and you can always derive it by saying that, what is the formulation that maximizes the entropy? And then say that this is a good idea, but I always question them. Why is maximum entropy if we need to start with them? So nothing. But yes, we need it. We need it. We definitely need it. Any other questions?
So how is the parameters W and P?
Oh, yeah. So that's actually exactly what we're getting into. So stay tuned. Any other questions? Okay, very good. So we exactly go on to the optimization side. That is, now we have the per example loss function. Then we know now that the data set level loss function is simply the sum of all these, for example, loss functions. Now what we need to do is to optimize this data set level loss function with respect to the parameters of our neural network, such as WY and BY. And that is often referred to as learning, which is completely wrong. So we shouldn't call it learning, because learning contains the entire, let's say, 5 steps that we are talking about today. Anyway, so for the optimization, you can imagine that there are so many different ways in which you can try to minimize the sum of these, for example, those functions with respect to WY and BY. That's true. There are many optimization algorithms. We're going to stick to one particular class of the optimization algorithms that can be, let's say, characterized as a gradient descent. So let's use the capital L, D, theta to indicate a data Y level loss function, which we're going to, we know now that this is really just a sum of the per example loss functions. And just for fun, we're going to say we're going to divide this by the size of the data set. Then any kind of constant division shouldn't change the optimization procedure, right? It's just they change the scale, but where the minimum are doesn't change. So we can just divide by whatever I want. But let's say we're going to divide by the size of the data set, because it turned out that actually gives us a very nice way to derive a computational modification version. And if you recall from, let's say, calculus 1 or some kind of calculus equivalent courses that you may have taken so far, gradient descent iteratively update the parameters by subtracting the gradient, the steepest descent direction from the parameter. So this is the gradient symbol. And then because the gradient computation is linear, so we can actually push it into the summation. So the summation is linear, so we can either way it works. Sum xy on the gradient of the per example loss function with respect to theta. So we start from some arbitrary theta. So we start from these arbitrary W vectors, arbitrary, let's say, minus values. We compute this data set level loss function, and then we're going to compute the gradient of this loss function with respect to those parameters, like the weight vectors and so on. And then we update each and every parameter following the negative direction of the gradient, because the gradient computes the steepest ascent direction, right? So that this direction that I can take a very small step, and I will guarantee to have improved this. So we are doing the minimization. So we use the negative sign here. Then it turned out that because our data set loss function is decomposable, so decomposable over the training per example loss functions, we in fact compute the gradient of the per example loss function with respect to the parameters, then we simply sum them. Now you see, why I wrote this is that either you sum them or you can say that you average them. The averaging has some nice properties, is that it's invariant to the number of items that, so the scale is invariant to the number of items that we are averaging, unlike summation. So there is a big issue here. We are now living in the so-called era of big data. And then this E, however, the one letter that is, it is big. Millions, billions, trillions. It's not that difficult to find a trillion size, let's say, data set these days. In order to make this small step, then if you recall from the calculus class, this gradient being the steepest ascent direction is only locally bounded, and then the neighborhood is in fact infinitely small. What that means is that you can't really trust this direction too far away from where we are. So we need to have a step size, or the learning rate that is tiny. So we make like small. In order to make that tiny one update to the parameters theta, we have to evaluate the gradient. We have to evaluate the gradient of a, for example, loss. Millions is like billions of times. Doesn't make any sense. This just doesn't make any sense. And then this kind of billions, trillions, like sure story, right? You just download the entire Wikipedia dump and then try to train a language model. That's already like billions of text, right? So it's very inefficient. But then thanks to having this does anybody have a charger for MacBook? USB Type-C? I swear last year was fine to like they do the lecture for 3 hours with the same laptop, but the batteries are really like the batteries are, you know, consumable. Thank you. All right, the lecture's now over. Just give me a second. All right, this. So it's not entirely sure if this can work. For sure. Yeah. Okay, all right. Wait. Okay. All right, so we're coming back up online. Just hold on, I need to share the screen. All right, now we are back. Yes, okay, we're back. All right, so the nice thing here is that we actually do have this averaging operation. What that means is that we can view this whole thing or computing this gradient as Monte Carlo approximation to computing the expected, for example, gradient over the distribution from which the data set was sampled. So what does that mean? So that each and every example in D, in fact, there was some, let's say, distribution, underlying distribution, data distribution from which we sampled, this was sampled, right? So this is your whole, all those the IID kind of thing. And then what that means is that assuming that there exists the kind of distribution, which is a standard assumption, we can rewrite this whole procedure of L E theta as in fact was approximating the computing the expected per loss gradient with respect to the parameter theta over the distribution that is the data distribution. So when we try to compute some kind of expectation and then it turned out that they're so complicated in general, what do? We use Monte Carlo approximation where we draw number of samples from this distribution over which we're computing the expectation and compute the value and average. Turned out that's exactly what we were doing. So in a sense, Another way to look at what this gradient descent was doing is to take the step in the direction of the expected per example, the gradient expected gradient of the per example loss function. And by thinking about it from this angle, it tells us that we actually don't have to use every single example from the data set every time we try to approximate this expected gradient of the per example loss function. That is, we can approximate it by, I'm going to say, using a small subset of the examples from the examples called mini batch. So we're going to call it mini batch. And then the size of this mini batch can be significantly smaller than the size of the entire data set. And we just go through it and to n, or actually, I'm sorry. X, Y, and the n, and compute the per example, the gradient of the per example loss using only these examples within this mini batch. And then this is how you get stochastic gradient. And SGD. And this is truly the workhorse of modern machine learning. Not only different, but the modern machine learning in this era of big data, stochastic gradient descent is the algorithm that is being used. And then the size of the mini batch can be as small as 1. And if you ask Jan LeCun, he's going to say 1 is the optimal size, but I'm pretty sure that's not true. But well, it's up to you to trust up to you to decide who to trust more. But I know I tend to trust Jan a bit more than myself. So there's a reason why I didn't give out those Turing words. Yes. All right. Now, in practice, we don't just create a random subset mini batch of the data set every time, but we partition this data set, large data set, into a small mini batches that are non-overlapping. And then we just go through them one at a time. And then we go through them multiple iterations. Although strictly saying, because it's the expectation that we're approximating every time, we should definitely use a fresh set of samples from this data distribution, but we often can't afford that. So we just go through these partitions of the mini batches. Any questions about the optimization? And this will be the last time we actually talk about optimization, because we're always going to define a per example function, make the and use the stochastic gradient. Nothing else. All fine, yes? Makes sense? All right. Now this has been the optimization. What is the next thing? Model selection, right? The model is a horrible, let's say, term to use, but you can imagine, as I said earlier, that we're going to try to find all the things that cannot be inferred from data. So anything that cannot be inferred from data, we choose them based on this model selection procedure. So above, in this optimization, we were optimizing these loss functions with respect to the parameters using data. So these parameterization parameters are inferred from the data. So that was the optimization's job. Now the model selection's job is that for all the other things that optimization cannot choose. Optimization cannot choose the parameterization and how we're going to define that. Because we don't know, we need that in order to compute the gradient to start with. So how do we choose that? Optimization cannot tell us which learning which step size to choose. Because that is actually not because it's always going to say that, yeah, let's try to reduce it to 0 or grow it to infinity. That's the only, let's say, sensible solution in that case. So it can't really tell us what to do about it. And then the size of the mini batch, you can't really tell us because we need to actually decide the size of the mini batch in order to compute the stochastic gradient or the expected or the approximation of the expected gradient as well. So what we need is to have yet another procedure that relies on yet another set of data points that does not overlap with this training set in order to select all those so-called hyperparameters. the modal selection in a more modern hipster name is the hyperparameter selection or the optimization. Then these include learning rate, how we initialize this data, or the size of the min batch and everything you can imagine. And for doing so, let's say this lambda is a hyperparameter. Then hyperparameter optimization can then be written down as we're going to minimize, we're going to find the lambda that's going to minimize, so this lambda hyperparameter that's going to minimize the expected per example loss function using the parameters that were found from the optimization procedure. It's a bit lengthy. So here, this is optimization. We try to minimize the expected per example loss function, which is the data set level loss function. Once the optimization is done, where this optimization procedure is in fact a function of this hyperparameter right now, for instance, learning rate. Once that is done, we now need to compute yet another expected per example loss of the instances using this found, let's say here. And here, this loss function can very well be different from the loss function that was used for optimization. Now, what I want you to look here very carefully is that there are two expectations. Expectation that is involved in training and an expectation that is involved in model selection. So this is how we're going to select the one that's going to minimize. And then these are not independent because this lambda is used to compute this expectation, and then this expectation was used to find the theta, and then this theta is used to compute this expectation. So these expectations are nested and then dependent on each other. What that means is that if we use the same set of samples from the data distribution for both expectations, there's going to be a biased estimate or the approximate estimate of this expectation. In other words, we have to have another set of examples drawn from the same distribution in order to do the model selection, and then that set is often referred to as validation set. So we use training set here, T. For this, we're going to use validation set. And then this is really important. Whenever you find the hyperparameters, you cannot use, or you should not, because you can use the same set to do the model selection, except that the hyperparameters that you find are going to be meaningless. Was there a question? So it's important to have this D prime. And then I'm not going to go into detail about the hyperparameter optimization because I just noticed that we actually ran over time. But there was a hiccup of like 2 minutes before, so I'm going to spend 1 more minute. After the model selection is done, what was the final stage? Reporting. What are we reporting? We are going to report how well this model that was optimized using the hyperparameters found by the model selection procedure. We want to see how well that works. Now, what does it mean for that to work well? Is we want to know on the expectation, what would be the per example loss of that model that was trained using the hyperparameters that were selected using the model selection. Now that means that we have 1 expectation, 2 expectations, and then for the reporting, we have yet another expectation there, right? And that expectation, so whatever we're computing, the inside of that outermost expectation is a function of the second expectation and the first expectation. So again, we cannot use the same set of examples to train, validate, and report. So we need to have at least 3 separate sets of the data points in order to report. And the most important thing about reporting is that we all tend to forget the purpose of reporting. The purpose of reporting is not to get 1 paper accepted or not to get your promotion on that. The purpose of reporting is to know how well this model is going to work in the future. So a lot of people forget the fact that the purpose of reporting is to actually know the future, right? To be, predictive of the future, and then use the same data set for model selection or even training. Now, as soon as you do that, you actually lose the predictive nature of this reporting or the test action. So it's extremely important not to use the test set or this reporting set for the purpose of the model selection or training or the optimization. So that's very important. And other than that, reporting is same as model selection, except they are more expectation. So that's going to conclude the lecture. Welcome back to the campus. There are lab sessions tomorrow, and the after the course sessions are prepared. And I'll see you all next week.